working on was called the standard form of a quadratic function. The first couple of days of this unit, we learned about the vertex form of a quadratic function. A number of things about that. We learned how you could go from y equals x squared to that through a series of reflections, maybe, stretches, and shifts or translations. But the most important thing was once we arrived at that vertex form, it was rich with information. It could tell you where the vertex was, whether the parabola opened up or down, what the axis of symmetry is, if it opened up, what the minimum value of y was and where it happened. All that information was at our fingertips. We could just look and see what it was. But we learned that if you expand this out, you can get a different form, which looks like ax squared plus bx plus c equals y. And it is important, I think, for you to understand that whatever the value of the parameter a is in the vertex form, that's the value of the parameter a in the standard form. That doesn't change. Okay? And what we learned is that other than a, there's one other piece of information that is available here. And that's that the value of c tells you something about the graph. Who can remember what it tells you about the graph of the quadratic function? Yeah. It's always the y-intercept, exactly. But let me write that down. This is the y-intercept. And the reason, there's a reason for that, and it's because the y-intercept is where x is 0. And if you were to put 0 in for x, this term disappears, because 0 squared will be 0. This term disappears because 0 times b will be 0. So it makes sense that putting in x equals 0 gives you the constant term, which is the y-intercept. Now, what we spent the bulk of our time working on was then the only way you can analyze a standard form of a quadratic function is to use your graphing calculator. We also looked at a word problem. We're going to continue to explore word problems today and tomorrow. In fact, for the rest of the unit. So I would like you to take a look over your work, please, and see if anybody has any questions, and I'll be with you in just a minute. All right, does anybody have any questions you would like me to go over from any of the practice problems? Remember, at this level, the responsibility is yours to make sure if you have questions, you ask them, which means the primary responsibility is on your shoulders to make sure you try these problems. I don't check homework, but don't let that give you a false sense of security that you don't have to do anything, because then you pay for it on an exam. So just a reminder. I feel as though I should remind people from time to time. Go ahead. 17? All right, McKenna, let's take a look at number 17. So Maria lives on a farm. Now this is, I'm glad you asked about this. This is a problem that we didn't quite get to. There's something similar to it that we're going to do today. But if I spend time going over number 17, the one that we do in our examples today will be that much easier. So Maria lives on a farm. She's going to build an enclosure for her animals. And she has 280 meters of fencing. And she wants to build it in that fashion where she's got 3 different sections. Now, by the way, your textbook is famous for saying use X for this. I'm not going to. I'm going to use W for that. And I'm going to use L for this. And your textbook is famous as well for having all of these parts. And I'm going to give you how the question would appear on an exam. What dimensions will maximize the area? I mentioned on Friday that this is called an optimization problem. To optimize something means to make it as advantageous for yourself as possible. So I used a number of examples. Here's one. We want to optimize the area. She wants as much area for her animals as possible. Okay. We will see in an example today that you want to maximize the amount of money that comes in. We will see in other examples later on that you want to minimize your costs in a business. So this is what an optimization problem is all about. Now, I mean, we can follow through the steps here, but the bottom line here is if you can come up with an equation that has area as a function of, I'm going to say, the width of the enclosure, and this next bit of business is kind of important. If you can come up with that, then what that means is you can translate this function to a graph. And if that function is quadratic, which it will be a parabola with a maximum. So using this as a width is no good. It doesn't maximize the area because you could use this as a width, which, I mean, you're kind of indifferent to. You're not as sad about it. You're getting more area. But the point is there's some width that is going to give you the maximum area. And that width, of course, is going to correspond to the vertex. And this is why we learned about the vertex form. So if we can come up with this function, we can locate the vertex, we can answer the question. What A, B, C, and D, and E are all getting you to do is they're walking you through it step by step. I'm just going to look up here and I'm going to say, well, the area of that rectangle is length times width, isn't it? That's got to be a good start. Area equals length times width. In math, in high school math, and also university math for the most part, unless you're going to get a math degree, your equations that relate variables in terms of a graph are equations that have two variables. If I said to you graph A equals LW, your brain would start to swim around in your head. Because how do you graph three variables when you only have two axes? Well, the answer is you could have a third axis, but we don't want to do that here. So we need to get rid of one of these variables. Let's get rid of, well, I won't say yet. We'll make a decision. In order to get rid of one of those variables, you need a relationship between the variables. Who can remember what we can do here? What's the relationship between L and W? It's a little more complicated than the one we did in class. But in general, can you tell me something about L and W? Could L be 100,000 meters and W be 1,000,000 meters? There's got to be some limit to how much fencing, right? The limit is 280 meters. Now, do you remember on Friday, if it was 280 meters, and I don't believe it was, but if it was, we wrote 2L plus 2W equals that number. Well, what we're going to have to write here is 2L plus 4W equals 280. And be very careful here. There's three sections, but there's a W here, 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 and here. You've got 4 W's and 2 L's that are used for fencing. Let me write that equation down here somewhere where I can access it a little bit better. 2L plus 4W equals 280. I think it would be easier to get rid of L, and here's why. If I divide everything by 2, I get L plus 2W equals 140. So, well, let me finish this part off and then I'll back up and show you something. Which means that L is equal to negative 2W plus 140. McKenna, does that make sense? Okay, so that is what's going to go here. So I'm getting rid of L. How many of you, just by a show of hands or a nod of the head, understand that if we were to rearrange for W, it would be more complicated? We're going to end up with fractions, aren't we? We're going to have like 1/2 L. I don't want to deal with fractions, which is why I've decided to rearrange for L. Now what this equation becomes is A equals L times, A equals L, which is negative 2W plus 140 multiplied by W, and we can simplify that. I can multiply that through, I'm going to get rid of this arrow. It's just getting in the way. We can multiply that W through negative 2W squared plus 140W. Is this a quadratic function? Yep. There's your x squared term. That makes it quadratic. Does it open down? Yeah, because it's negative 2W squared. So there's a maximum y. But y is area. There's a maximum area. How do we find out what the maximum area is? We're going to graph this on our calculator. There is an algebraic way to turn this into this. Well, I guess it's W, not X. There is an algebraic way to turn it into the vertex form, but you don't know that yet. So we have to use the calculator. What do we have? Negative 2x squared. I mean, we can't put W there. Our calculator thinks in terms of X. Plus 140x. This is good. I'm glad you asked, because we're going to get lots of practice with this type of question, and we need lots of practice. Zoom standard's probably not going to cut it. It's probably not. Okay. But you want to look at the numbers in the question. If we have 280 meters of fencing, could you use 30 meters for the width? You could. Could you use 280 meters for the width? No. All that's telling me is I know that it's somewhere between nothing and 280. I mean, you can't use 280, but I'm going that far anyway. So I am going to, this is one of the most difficult things I find myself having to teach a group of students. I'm going to first of all say, I'm going to go from 0 to 280. I know it's not going to be anywhere near 0 for X to get to the maximum. We're talking about this point right here. I'm going from 0 to 280. I know it's nowhere close to 0 and nowhere close to 280. I'm pretty sure. But I'm going to choose those numbers. I don't know if anybody remembers, but I'm going to ask, what can I do on my calculator to find out how high I should go? Yeah. Go to the table, sure. I'm going to set up my table to go from 0 to 280. Let's go up by 50. I don't know, 40. You can go up by whatever you want. So I'm going to set up my table. This is perfect. To start at 0 and go up by 40. And then when I go to my table, I'll be able to track the different y coordinates that are happening. And that will give me an idea of where to go for y. So, oh, right away, look at that. I go at 0, I get nothing for the area. At 40, I get 2,400. And then it's already in the negative. That tells me it's someplace between 0 and 40. It's already dipping below the x-axis once you get past 50 or 60. So maybe I'll reevaluate that and go up to 60. And now maybe we should reevaluate the table. Let's start at 0 and go up by 2, 5, 6, some number that's smaller. I'm going to go up by 5. There we go. Look at that. It's going up. It's going up, up, up. It reaches 2400. It reaches 2450. Then it goes back down to 2400. So the maximum has got to be around 2450. And some of you might suspect it is 2450. Because it's right in the middle of those two 2400s. But I can now go to my window setting and say I'm going to go up to, let's go up to 3 grand. That will include 2450. And now, McKenna, when we graph it, there's a nice looking parabola. How do we find the max? We go to our calculate menu, choose maximum, put our cursor to the left. Whoops, I'm gonna have to do that again. I hit enter too many times. Put our cursor to the left and hit enter once. Scroll to the right. Hit enter again, hit enter a third time. So what is this telling us? Well, that graph I had earlier, I said that this point was important because that width gives you the maximum area. So this is the maximum area. And what is the width of the enclosure? The width is 35 meters. I'd like everybody right now to figure something out for me. If this is 35 meters, what's that? And there's at least 2 ways you could figure it out. Hand up and down when you have an answer. Okay, and then just keep doing that. What'd you get? 70. How did you get 70, Grace? Pardon me? Yeah, she used the formula. The formula was, and there's lots of ways to do this. We had negative 2w plus 140. Was that it? So we got the width of 35. She put the 35 in there, and it gets you 70. Anybody do it a different way? What'd you do? Right. You could also say the area is the length times the width. So if we know the area is 2450, divide that by 35. What I did was I took 35 plus 35 plus 35 plus 35, and that gave me 140. And then I said I had 140 meters left over, and it's split between 2 pieces, so it's 70. Anybody do it that way? Yeah. And there's all kinds of ways you could do it. By the time you get to the answer, you've got all these formulas floating around and all these relationships that you can use. Anyway, McKenna, is that okay? All right. We're going to move on right now. We're going to continue to do basically what we did yesterday. There's just so many types, not yesterday, Friday. There's so many types of problems, I don't feel the need to squash them all into one lesson. I think in order for me to teach you as well as I can, sometimes we use up a lot of time anyway. I mean, let's just take our time and break things up. So we're analyzing quadratic functions in standard form, which is what we did on Friday. And we're going to continue to look at applied problems. Let's just jump right in. A quadratic function is given by this: y equals 2x squared plus bx plus 10. and the quadratic function passes through the point 4 comma negative 6. Let me tell you two things about this question. You've never seen this question before. The second thing, you've seen this question before. You've seen questions like this before. It's almost identical to things we've learned. You just haven't seen this specific type of question, this specific variation. The hint I will give you, and I want everybody to think about this so I don't want an answer, is this is the hint I'm going to give you. This is called something in the context of this question. And to find the value of it, we do the same thing we've done in other questions like this. How many of you know what I'm talking about? How many of you don't know what I'm talking about, but you have an idea of how to find B? Okay. Well, what this is a missing parameter. How many of you didn't know how to find B a minute ago, but now you do? Okay. For those of you that still don't, what do you always do to find a missing parameter? You load in an ordered pair for x and y. So this problem is just a math problem. It's not a parabola problem. It's a math problem. It's an algebra problem. So we load in x and y. And again, I want to explain something. What it means to say the graph passes through 4 comma negative 6 is that when x is 4, y ends up being negative 6. You put in 4 for x. And you get negative 6 for y. And you eyeball this equation, everybody. This is a really grade 9 equation at best. You can simplify this quite easily. Negative 6 equals, double check my arithmetic here, please. 2 times 4 squared is 32. Pretty sure, but you know, my brain gets tired as well sometimes. 4b plus 10. This is like stealing candy from a baby at this point in time. You can just add the numbers together and solve for b. I get negative 6 equals 42 plus 4b. So I can subtract 42 from both sides and get 4b equals negative 48. Divide both sides by 4 and get b equals negative 12. Yes? Okay, we could check this, because if b equals negative 12, then the function should be y equals 2x squared minus 12x plus 12, plus 10. I'm just putting in the negative 12 for b. Let's graph it on the graphing calculator and see if it passes through that point. 2x squared minus 12x plus 10. I'll go zoom standard because 4 comma negative 6 is in that domain and range of negative 10 to 10, negative 10 to 10 for x and y. I can go trace and enter the x coordinate rather of 4. I can see the y coordinate is negative 6. I could go to my table, check it out there as well. It's a pretty basic question. Let's try another one. We're only doing 4 examples today. A frog that's sitting on a rock jumps into a pond. And you're given this formula for the height of the frog above the surface of the water in terms of time in seconds. Now, we want to answer all of these questions based on the graph. I hope it's reasonable for you to understand that this is probably what the graph would look like. where this is h equals 0, which means that this is where the nice blue water is. This is the rock, or whatever the little froggy is on. I'm going to jump in there. If we can get this graph on our calculator, then locating this point will allow us to find the height, or will allow us to find the maximum height of the frog. Locating this point will allow us to find the height of the rock. Locating this point will allow us to find how long the frog is in the water. This question is all about using your graphing calculator. By the way, what is the height of the rock above the pond? Without using your graphing calculator. 25 centimeters, because that's the y-intercept. It's where the frog starts. So we know this is 25 centimeters. The y-intercept is the constant term. Okay, let's graph this. So y is equal to, it's y in my calculator and h on paper, negative 490 x squared plus 150 x plus 25. And we're going to get the window settings the same way we did for the area problem. How long do you suppose the frog is in the air? Is the frog in the air for 25 seconds? Is this a magical frog, a flying frog? No, maybe a second or two. So I would probably, this isn't a commitment, I'm just putting it up here for you to see. I would go 0 to 2. I suspect it's less than a second. Now, how are we going to see what kind of y values or heights it has? We'll set up the table. But let's set it up in more detail. Let's start in table setup at 0, and let's go up by 0.1. When I go to my table, now I'm tracking the height of the frog. Look at this. The height is 35, 35. The frog's already on its way down at the 0.4 second mark. And you can see that by the time we hit half a second, the height is negative, which means the frog is in the water. So now what I can do is say, I'm not going to go from 0 to 2 seconds. Let's go 0 to half a second. Now, when I go back to my table, the maximum height appears to be around 35 centimeters, right? So I'm going to go up to 40. But, so this is in the window setting. I'm not going to start at 0. I'm going to show you what happens if you do start at 0. So just leave your calculator alone for a second. If I start at 0 and then graph it, I get a beautiful graph, okay? It's lovely. But when I go to find the x-intercept to answer how long the frog is in the air, when I go to find the x-intercept to find out how long the frog is in the air, my calculator is going to ask me to put the cursor to the left of the x-intercept, which will be here. And then my calculator is going to ask me to put it to the right of the x-intercept, which is down here. So my recommendation is anytime you know ahead of time you're going to find x-intercepts, start at a negative value for y. All right. We're just about ready to answer this question. Let's start at negative 10. It doesn't matter. Will that be enough room for me to put the cursor to the right? Sure. So we've already established the height of the rock. If I go trace 0, that gives me the y-intercept, 25. If I want to find the time the frog is in the air, which is part B the time in the air? Okay. Then I'm going to go to my calculate menu and choose max. No, I'm going to choose 0. Put my cursor to the left. Not quite sure what happened there. Put my cursor to the left. Then put my cursor to the right. Did I go up to 0.5? Was that what I went to in the window setting? I think so. And then hit enter a third time, 0.42 seconds. And you can scroll around to do that, right? You don't have to pick an X value. So about 0.43 seconds or 0.42 seconds. I guess we would round to 0.43. What's the maximum height of the frog, and how long after the frog took wing did he or she reach the maximum height? Well, we're going to go to our calculate menu again and choose maximum. Put our cursor to the left. Put our cursor to the right. And then hit enter. The maximum height is 36.5 centimeters. I'll say 37 centimeters. I guess 36, bless you. 36 centimeters, and it happens at 0.15 seconds. Again, this question is all about you learning how to use your calculator efficiently. Any questions with A, B, or C in question 2? All right, after our conversation with the question that McKenna asked about, this next example should be child's play. Billy Bob has 300 feet of chicken wire. Billy Bob has pit bulls, poodles, alligators, and bunnies. Suffice to say, none of these critters get along with other species, so he needs an enclosure that has 4 separate pens. If I call this W, then this is W, this is W, this is W, this is W. This entire distance is L, and there's an L up top, and there's an L below. So, if you want to maximize area, what you do, it says find the dimensions of the pen that will maximize the area. Then you start off with a formula for area. A lot of learning math is about recognizing patterns and questions you've seen before. I have a question for you. I want everybody to think about it for a minute or so. What's wrong with that equation? There's nothing mathematically wrong with it, but what do we have to fix to move forward? So put your hand up and then down if you know what we got to do here. Okay. Remember, this goes to the idea that if you want to maximize area, then you need to be able to think of a graph of area as a function of a variable, one variable. So what do we have to do here, Lucas?
You have to get rid of one of the...
I got to get rid of L, or I got to get rid of W. How am I going to do that?
Put in coefficients.
We need to be more specific than that. That's just a little too general. I know that you know what you need to do, but how can we put this into words? What is it we need to do here? Right. Make an equation relating all of these W's and L's. So we're going to take 2L plus, oh, wow, 5W equals 300 because Billy Bob's got 300 feet. Which do you think it would be easier to rearrange for, L or W? I think we're kind of hooped either way, aren't we? We're going to have fractions. If you rearrange for L, then you're going to have to divide everything by 2 at some point. So you'll have 5 over 2. If you rearrange for W, you're going to have to divide everything by 5, so you're going to have 2 over 5 somewhere. I don't think it really matters. Let's rearrange this for L. 2L equals negative 5W plus 300. Divide everything by 2, you get L equals negative 5 halves W. That's negative 5W over 2. And then 300 over 2 is 150. This is what we put in. Let me move that down so you can see it a little better. This is what we are going to put in for L into that equation, giving us A equals that L, negative 5 halves W plus 150 times W. Multiply that W through, negative 5 halves W squared plus 150 W. Look, the hard work is done. Well, the math 20-1 work is done. Now you got to fight with your calculator to find the vertex of this thing. So I'm going to enter in the function. Negative 5 divided by 2 times x squared plus 150 times x. And I'm going to try something here. I don't teach this to you initially because I think you can learn to be lazy and it doesn't always work. I think it might work here. If you go zoom way down near the bottom, you can't even see it. There's something called zoom fit. And what your calculator does, I've never been able to get a straight answer about this, but I think what your calculator does is it takes a look at all of the intercepts and the important features of the graph and it zooms to see all of that. See, and it's thinking right now. It was doing a lot of thinking there, wasn't it? Now, you can see that it didn't work in this case, but you can also see that the calculator is going, the graph is going up. So we could go to our table. I think zoom fit was kind of a dead end here. It just keeps going up. I guess we could go to our table set and start at 0 and go up by 10, maybe. It's going up. Oh, look at that. Actually, I lucked out, didn't I? That's a nice table setting. Do you see how those numbers in the table translate to something that's going up and then down? So zoom fit was a waste of our time there. Let's go from 0 to 60 for x and from 0 to 3000 for y. 0 to 60. Yeah, that wasn't a very intelligent zoom setting when it went zoom fit. It just look at the little piece. And what did I say? 3000? That table's a real lifesaver. It really is. If you understand how that table's operating, it's a great way to get the right window settings. Find the maximum. Left, enter, right, enter, enter. Oh, 30, 2250. So don't forget, everybody, that this is area and this is W. So the maximum area and the width that produces it correspond to the ordered pair for the vertex. So what's the maximum area? 2,250 square meters. What's the width? 30. Find the length. Well, this is what I asked you to do in the example that McKenna had asked about earlier, right? If the width is 30, can you find the length? Some of you took the area divided by the width. I want to say 75. Is that right? So if you take 2250 divided by 30, you get 75. Some of you went to the equation that we used for L, which would have been L equals negative 5 halves W plus 150. Thank you. And if you put in the 30 for W, you'll get the right length. Some of you, like me, just said, well, if I have 30, 30, 30, 30, 30, that's 150. I've got 150 feet left. Divide it by 2. I've got 75 for the length. So what I would say to you is this area problem is a classic problem. You need to know how to do it. Could be a good written response question for an exam. Any questions with that example? One other example we're going to look at today is a classic type of problem that you're going to see again and again and again, and it also is one that you need to know how to do for an exam. So you have a store that's selling reusable water bottles for $8 a pop. At this price, they sell 100 per week. So if they have lots of stock and they put them at $8, that's what they advertise them for, they sell 100 items. Now, you and I know that if you charge more for an item, fewer people will buy it. Does that make sense to you? And if you charge less, more people will buy it. But just because you have fewer people buying something doesn't mean you make less money. Let's look at what this is saying. Every $2 increase, the manager sells 5 fewer bottles. So let's just talk about what's going on here without talking about quadratic functions or equations or anything. The price per bottle is $8 and you sell 100. So your revenue is the amount of money that you take in, is $800. I hope everybody sees where I'm getting 800 from. Pretty straightforward. You got 100, you sell them for $8 each. It says when we increase it by $2, so now we're going to try selling it for $10, we lose 5 customers. It says you sell 5 fewer water bottles. That would mean we have 95 here. I've upped the price, I've lost customers, but as a business owner on some level, it's not that I don't care about the customers, but the bottom line is money. When I multiply those together, I get 950. So the revenue's going up. If I were to, instead of going up like that, what if I did this? I'm going to ask you to do some problem solving here. I've jacked the price up $20. And the question says every time I bump the price up $2, I lose 5 people. So I want you to see if you can figure out how many people I lose when I bump the price up $20. I think I lose 50, don't I? Because $20 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I lose 5, 10, 15, 20, 25, 30, 35, 40, 45. I lose 50 people. This is only Out of 100, I've only got 50 loyal customers left. What do I get when I multiply those? I believe I get 1,400. I'm still making more money. It's still going up, isn't it? What if this is not how you're going to do the problem. I'm trying to illustrate a little bit of economics to you. What if I did this? Whoops. I guess I can get rid of that. What if I went from 8 to 48? That's a pretty, you'd really have to do a hard sell on that water bottle. It's $48, but man, it's a good bottle. What this person is doing is recognizing that, and this is true, in society, there are always some people that are willing to buy anything. That's how you can get rich, if you got the right product. This is an increase of $40. $40 is 20 $2 increases. So how many customers they lose? They lose 5 people for every $2 increase. How many people they lose? Everybody, right? 100. So they're left with nothing and their revenue is 0. Somewhere in here the revenue has to go down. It's going up and then it has to go down. This is going to be, that's R for revenue. It's going to be something that looks like that. And our goal is to determine what price you should charge to get the maximum revenue. We're not going to do it this way. We're not going to do it with a table. We're going to say, so now we're into the equation aspect of this, that the revenue is going to be the number sold multiplied by the price per item. But we have to introduce a different idea here. We're going to let X equal the number of $2 bumps. Okay? So if X is 1, they're increasing it by $2. If X is 2, they're increasing it by 4. Well, the number sold, we'll do the dollars per item first. We originally sell them for $8. We're going to add $2 for every bump in X. For every single X, we increase by $2. So let's go back to this again, because this is a little tricky. If X is 1, it goes up by $2. That's why we go 2 times X. 2 times 1 is 2. If X is 4, it goes up by $8. That's why we would go 2 times 4. 2 times X would be 8. Are you with me on that? Okay. The number sold is 100, and it's going to go down. By what? What's it going to decrease by? Check. 5x. Because for every x, the price goes up by 2, but the number of people go down by 5. Now, would you agree that if you multiplied that out, it would be quadratic? Let's multiply it out. First, outer, inner, last. First is 800. You guys keep me honest here with my multiplication. Outer is 200x. Yeah? Good. Inner is negative 40x. And last is negative 10x squared. If I write this in standard form, I put my x squared term first,